It is my pleasure to introduce our next speaker. Dr. David John Gagne is a machine learning scientist and the head of Machine Integration and Learning for the Earth Systems Group at the National Center for Atmospheric Research, NCAR, in Boulder, Colorado. His research focuses on developing machine learning systems to improve the prediction and understanding of high-impact weather and to enhance weather and climate models. We are really excited for your talk, and we're very curious what you have to share. Please take it away.
Thank you for the introduction, Marlou. Excited to be here and kind of give a broad overview of AI for atmospheric science. So the kind of big topic area I want to focus on with this is how AI can help predict weather and climate disasters. As I'm sure you're aware and have experienced, the weather and climate disasters continue to cause major impacts globally. There's a couple like major weather disasters that happened kind of in my neighborhood. So one just down the road from me, we had this a couple of years ago. We had this giant wildfire called the Marshall Fire that destroyed quite a few homes, sort of in the towns east of Boulder and south of Longmont, where I live. It was an extremely impactful disaster on a kind of unusual day for a large wildfire, but basically had all the wrong things come together to make for an awful scenario. We also recently had a pretty impactful hailstorm that hit just kind of south of my house, where basically had this strong hailstorm kind of go through the northern suburbs of Denver and barely missed the Denver International Airport. And with both of these events, while overall we've had a lot of improvements in weather prediction, and we've been able to kind of mitigate a lot of major impacts by giving people warning to take shelter or evacuate or kind of take other protective actions. What we've been finding is that the rate of improvement in our weather predictions has been slowing. Some of this is because of we're kind of reaching some of the limitations of our further growth of computing, and with our kind of traditional weather prediction models, it's harder and harder to optimize them. I've also seen that the benefits of improved weather prediction have also not been equally distributed around the world. We have really good forecasting systems in let's say the North America and Europe, but some of those systems don't we still have major impacts of people just not being able to detect major rainfall events or heat waves or other stuff in time for them to take action, and there isn't all the infrastructure to disseminate those weather messages. At the same time, we have climate change occurring and increasing the frequency and severity of things like heat waves and extreme precipitation events. So it means areas that were kind of all their infrastructure developed for a certain kind of set of weather scenarios are now experiencing different ones, and that's causing all kinds of problems that we're having to adjust to at a fast rate. So with these kind of challenges all mixing together right now, where does AI fit into the equation? I think it can offer a path to help with further weather prediction improvements, but also with the dissemination of weather information. It can also potentially help with both understanding from the expert perspective as well from the general public perspective of how to best use weather data for various problems. And in this talk, I'm going to cover a few ways it can be used for weather and climate prediction, and also what are some of the challenges and pitfalls of the use of AI in this context. So kind of to start off, why should you embark on the AI Odyssey? Kind of in general, AI models are often used for tasks that are kind of intuitive for humans to do or describe, like I want to find the sailboat in this image, but are hard to describe formally. Before kind of AI machine learning systems became popular, recognizing things in images was really hard to do, and couldn't do it consistently well. And we're finding now there's a broader and broader array of tasks where AI can do about as well as a human or better than a hand-coded system, especially in cases where the AI system can perform the task approximately as well, much faster, more consistently, and it can be done at scale. And with these properties, there are a lot of tasks that kind of fit into this realm of AI, and even ones that may not exactly fit these tasks that AI could, I think, is showing promise of being able to address. It comes with this cost, of course. So we'll cover a bit of both. So to kind of cover some like terminology with this, what is AI versus machine learning versus deep learning? AI, at least when I'm referring to it, is kind of the catch-all term for the systems or methods for computer systems to perform human tasks. So say you need something to get you from one place to another, that the system we're going to use is the car. So AI in this case is the car. There are a lot of different ways to do AI that basically developed over the past century or so. But the kind of most popular way to do this today is using the class of methods called machine learning. And these are computer algorithms that learn by reviewing large amounts of data. So learning in this case is usually updating weights or changing the structure of some kind of mathematical model. And at a lot of the heart of current AI systems are one or more machine learning models that are then connected to other parts of your AI system via usually more traditional programming methods. And then within the class of machine learning, what has driven a lot of the innovation in the past decade or so is deep learning, which is a subclass of machine learning that features neural networks with multiple specialized layers for encoding all kinds of different information relevant to this problem of space and time information, but it could also be audio, image, video, genetic sequences, what have you. And you can think of deep learning as a very specialized type of engine, or like you had a really powerful engine. It's not necessarily the best engine for every task, but it can, but when for tasks it's specialized for, it can do really well. So there, within the AI machine learning, there are a lot of different flavors of AI depending on the kind of task you want to use it for. So at a high level, we can start with classification. A lot of AI tasks can be reduced to predicting the probability or the label of the outcome for a given task, given data. So this is like the cats versus dogs. Another flavor of AI is regression AI. Basically, instead of predicting a label, you want to predict a continuous value. And in this case, usually given a certain set of inputs, what's the most likely continuous value in that situation. So it's like what's the temperature going to be tomorrow, or like how much rainfall, or how bad is the tornado going to be. And then kind of building on both regression and classification AI is generative AI, which there's generative AI, the big buzzword of like ChatGPT and stuff, but the reason it's called generative AI is that you're generating potential solutions to a given problem. So it's more of a stochastic sampling of some kind of distribution. And that can be done by either sampling what is the next word in the sentence, or what is the next pixel in this image. There's a lot of ways to frame this so you can generate lots of different kinds of plausible answers. So with these different flavors in mind, there's a lot of ways we can use these AI systems. So I'm going to cover a few that are in the realm of more in realm weather and climate tasks. So one that where a lot of AI has been used like for a lot of tasks, but in particular for weather prediction, is object segmentation. So the idea is you want to look at some kind of image or field and find things of interest. So in this case, we're looking for the red areas are tropical cyclones, kind of looking for the centers of those. The blue contours are atmospheric rivers. So if you want to basically look at an image and find these, then you can track the properties of them over time. Are they getting bigger or smaller? How are they moving? There's a lot of basically large weather data sets where one wants to understand it, and the first step is finding the interesting things in it. Once you have your features, you can then apply other AI methods to diagnose properties about these images. So in this example, we have a satellite image of a hurricane, and we want to figure out how intense it is. So we train our neural network to look at properties of the hurricane image and then match that to an intensity, because more intense hurricanes tend to have like kind of a deeper eye and colder clouds and more of a symmetrical structure. So we know there's a relationship, and now we can automate the detection of those patterns. But we want to move beyond just like detecting things, images, and actually predicting the whole image. So this is where a lot of exciting work is going on in the space of AI weather prediction. So we can take the whole atmosphere, basically all the different atmospheric fields, and we can have our machine learning model predict the next state of the atmosphere. So what's the atmosphere look like in 6 hours? And then we just keep doing that over and over again. If we use the same fields, we can just keep feeding it back into the model and then see how the AI weather forecast evolves. This is also how physics-based numerical weather prediction works, except that instead of an AI model, you have a bunch of partial differential equations you're trying to solve in a discrete form. You can also do this not just at the full model level, but also at the process level. So if we want to model how just one aspect of the system is done, we can kind of make hybrid models that use both traditional physics and AI systems. And these are promising because they're a little bit more interpretable, understandable. They're also harder to maintain because there's more differentiated pieces. And no matter how we generate our AI models, we often need to map from kind of our weather variables to something that is more related to human impacts. So this is called post-processing or bias correction. So whatever our gridded model is, we then want to feed our predictions into some other model that then predicts things like extreme rainfall or the probability of a tornado or hurricane happening. And these models, if these models can learn behavior about the biases and issues in the numerical weather prediction models, then they can make improved forecast and derive better impacts. So from there, once we have like our kind of problem set in mind of what we want to do with our AI model, we need to gather data for it. There's usually some different paths you can take. Each of them have their own issues. One is using existing data. So if you have a long archive of existing data that's already freely available, then you can kind of this is the often path people start with. Just there's a lot. Weather and climate have lots of giant data sets. The challenge is that not all of these are well adapted for AI systems, so you have to do a lot of processing of it, and there may be issues because the data wasn't like collected for your purpose. It was usually done for something else. So in some situations, you may want to gather your own data, either to supplement the existing data or to have more control over the process. And this can be quite beneficial when you basically have a fixed window of what you want to do this and where you have the resources to do this. The challenge is if you want to learn more about the past, this is often not a kind of feasible route to go unless you're like recovering old chip logs or ice cores or other things that are proxies for what happened long ago. However, again, there are limits and challenges to that. This is where kind of your scientific knowledge comes in, or if you're collaborating with a domain expert who knows kind of that area, you can kind of figure out what's the best path. Finally, you can also just generate synthetic data, so we can like run our numerical models and with different forcings and initial conditions, and we can make or we can use like more mathematical models of a system. So like there's these idealized models that represent chaotic dynamics. There's ways to do that. These are easy to repeat and generate. You can generate as much data as you need, but sometimes that generation process is expensive and it's still you're in model land, not in the real world. So that can also affect how well any models trained on the data can generalize. So everything has its trade-offs, basically. So I'm going to stop for a second and have an audience question. So this is like, there's not really a right or wrong answer on this, but what aspect of AI systems do you think offers the greatest impact, positive or negative? A, answering questions faster, but only approximately, as well as other approaches. B, providing more consistent answers. C, general purpose algorithms at wide scale. Or D, finding previously unknown patterns on large data sets.
Please share your answers on Discord. I see multiple people sharing answer D, 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 more D, more D, all of the above.
For this particular question, I'm not surprised that most people pick D. It's definitely the most exciting problem. It's also one of the hardest ones to do in practice. Basically, AI algorithms are great at finding things that sometimes you already know, and some of this is how you analyze data. Sometimes the unknown pattern is some kind of artifact in your data, like based off of how you gathered your data, which is also something one has to be very careful with, because there's a lot of ways to inadvertently introduce patterns into your data set. So something with what people are striving for, but also where it's easy for both the analyst and the AI algorithm to go wrong. So next, I'm going to kind of jump into a little bit of like how do a couple of these major AI algorithms work. So first, I'm going to focus on are decision trees and their kind of derived models. So the decision tree is at its heart is a fairly basic algorithm. You start with a series of decision nodes, which is a question of like if you have some kind of variable and a threat and some kind of numerical threshold associated with that variable, you can say yes or no to a question, and then if you, depending on the answer, you go down a branch to the next decision node, and then you continue to follow that until you reach some kind of leaf node. And then the prediction at the leaf node is derived by calculating the relative frequency of each example type. So in this case, you follow down the yeses on both of these, you get a 76% chance of large hail. But if yes and no, it's only a 6% chance. So when these decision trees are built by the kind of decision tree growing algorithm, you're trying to pick answers that lead to the biggest difference between your two outcomes from a given node. And there's ways to measure that. And to do this, you have to kind of search over a lot of potential questions. So that's that can be the somewhat expensive part of decision trees. The great thing about these algorithms is that they do feature selection. So if you have a bunch of different possible input variables, the decision tree will pick the kind of the best one that works on the training data. And you can use this to filter out a lot of irrelevant variables if you don't know what variable is the best one. The downside of decision trees is that they're basically, because they have this like step structure and kind of are breaking your data into different regimes. If you have, they're really great for discontinuous data, not so great for smooth data. Like if you have like a linear fit, you should just use a linear regression. Decision tree will give you this like kind of stair step pattern if you use it there. The decision trees are also by themselves very brittle. So like a slight change in the data may result in a different threshold or a different variable being picked as the most relevant one. So the tree structure can change pretty significantly. That said, like some of these variations are within the realm of plausible outcomes for a given data set. So if you do some perturbations to the process to add some randomness, in particular resampling your training data for each decision tree and only not going through every single possible variable, only picking a random subset of them, you can so resample the training data. Then you have an ensemble of decision trees that each has a slightly different set of branching patterns. You average the predictions together, and then get your kind of smoothed out prediction. You get the algorithm called a random forest. And this algorithm, I think it's like this, considered the second best algorithm for just about every problem. It's easy to fit. It's very robust to like noisy missing data, finds fairly robust relationships, and it's pretty easy to tune. So a lot of people use these even today for a lot of machine learning problems that are just on tabular data. The other popular decision tree algorithm is called gradient boosting. So this is another decision tree ensembling algorithm. The difference between this one and random forest is that instead of the ensemble being each tree being trained independently, you first fit one model on your original data, and then your second model still uses the same training data, but is instead of predicting labels, it's predicting the residuals, or the basically difference between the correct labels and the or basically the difference between the correct answers and the predictions from the first tree. And then you just keep adding trees, and then you have a kind of weighted a weight you put on each tree that then basically gradually your trees you have a set of small trees that converge toward the right answer. These algorithms basically require a bit more tuning, but often will like for any tabular data set tend to get the best results. So for those of you who have maybe gone to like Kaggle or other machine learning competition platforms, if they're not using neural networks, often packages like XGBoost or like GBM are being used by the participants to get a really good result. So yeah, if you have tabular data with lots of variations and kind of noisy inputs and lots of variables, the decision tree and ensemble approaches work quite well. They can even sometimes work on image data if you're kind of treating it as like each column or area as a point. There's a couple examples of this. So there's a couple algorithms used in the weather space. One developed at NCAR is used to estimate fuel moisture content. So basically, how dry are the plants in a given area? Basically, like taking satellite data and other weather prediction data, we can combine that together with the decision tree. Like basically, get lots of variables and find the most important ones. We can then estimate just what the fire potential is. So the redder areas basically are drier, and if a fire were to happen there, the fire would spread more quickly because the plants are will catch on fire that much more quickly. And so this was done using a random forest. Our other algorithm is called NADOcast. This also takes in lots of variables from different weather prediction models and uses them to estimate the probability of hail or tornadoes. And in this case, it kind of, well, on the same day when we had the big hailstorm in South Denver, it did have some potential for hail in Denver, although the highest potential was further south where there was in fact hail, but the highest impact with it was kind of in our Denver metro area. So these are a couple ways you can use it. There's lots of other ways, of course, but I want to highlight a couple big examples. And then for the next audience question, based off of how I describe these algorithms, what kind of data relationship will be a poor match for decision trees? A, data that has thousands of independent input variables. B, plots of input versus output showing a smooth curve. C, data contains features of noisy and missing data. And D, data contains discontinuous regimes of sharp changes in outputs.
Share your answers again on Discord. I see various answers coming in. B, C, B, C. No A or D so far. People from all over the world are answering, whether it's from US to Kenya to India to Europe. I see more B, more C, Mexico, Argentina. I see Togo, Turkey. Okay, there seems to be consensus around B and or C.
My intended correct answer on this one was B. So as I mentioned, the smooth curve like is not something that is modeled well with decision trees. Basically, you want to use a more traditional regression approach or a neural network, which is also, as I'll explain, a bunch of regressions stacked together. Random forest or decision tree type algorithms are actually can be. I mean, C, I guess could be correct. One way decision trees are fairly robust to noisy or missing data is that the labels that when you get to a particular node are derived from just the labels in your training data. So if you have really wonky values, decision trees don't really extrapolate outside of their kind of training value training domain. So you could still get a bad answer with noisy or missing data, but you could still find your way through the tree to a, like, depending on your how you imputed your data, and get something that's a not completely unreasonable value. And with noisy data can basically on the ensemble methods, especially things like random forest, help balance that out because you pick different variables. So if some of your variables if they're a little bit noisy, like maybe other ones will compensate for them. But yeah, so B, I think C is definitely I think would also be I think a good match, but I don't think I explained it this property as well in the discussion. So I can understand why people pick C. So next we'll move on to neural networks. So the other so with neural networks, basically these algorithms drive a lot of the modern machine learning revolution. And what they come down to is at its heart quite simple. So there's a set of artificial neurons where you have some set of inputs. You basically take your inputs you like pass them through a bunch of hidden layers of these artificial neurons, and then you have some number of outputs that come out of the model. Inside each artificial neuron, you have a set of weights that are applied to each of the inputs, and then you sum the weights times the input plus some bias terms. So this is just a linear regression. The reason why this isn't just a giant linear regression is that you have a nonlinear activation function that basically modulates the output of this regression. And it is done, and there's a lot of different ways to choose this activation function. A lot of the ones that are used in modern neural networks use something called the rectified linear unit, which basically passes through the information untouched if it's positive, and then sets it to 0 if it's negative, which basically gives you a sparse structure to your model and allows it to kind of produce branching patterns, but in a smooth way, kind of similar to a decision tree, but otherwise can still pass through a lot of information. There's also other variants that have other properties associated with them. And so like depending on how you want your neural network to behave through your space of models, you can choose different activation functions. Also how much you want it to learn. So the ReLU is chosen because it can pass the information through forward and backwards, which I'll explain why that's important in a second. So then we have the structure. How do you train this model? So you start with we call a mini batch. So you take a random sampling from your data, you send it forward through your network, and then out from your network comes a prediction. With that prediction, you then compare it with what the actual outcome should have been, and you calculate your loss. So basically, an error function could be anything like mean squared error or entropy or any other kind of numerical comparison. These can get quite complicated if you want to add in other terms that look at different properties of the predictions and how they're correlated with each other, or even properties of the model weights and stuff too. But anyway, you sum that all together, and then to update the model, what you do is you calculate the gradient with respect to every weight in the model. So a gradient in this case is just the partial derivative of the loss with respect to that weight. And once you calculate, to calculate this, you have to use basically the chain rule from calculus. Basically, what it means is that the weights, the gradient for the weights in layer 1 are dependent on the gradients from layer 2 and on the output. And so you can then you basically do this sequentially backward through the model, and that's why it's called back propagation, is because you have to back the weights through. Once you have those gradients, you then use something called the optimizer to combine the current weights and the gradient to come up with a new estimate of what the weight should be. The optimizer usually contains information about something called the learning rate, which you multiply, how much should I change the weight at a given step. And then sometimes you have other parameters that describe keeping track of those changes in the weight, so that you're not changing it too drastically at a given step. This gradient, it also depends on what activation function you pass through. So the ReLU is special in this regard because it has the derivative of the ReLU when things are positive is the same value. So other activation functions before that had an issue where the strength of the signal would be decreased every time you pass through a hidden layer, and thus there would be not much information to learn earlier layers in the network. So most neural networks were shallow, but ReLU helped fix that. Some other changes in how neural networks are structured also help fix that, which is why we can do deep learning models now. So with this kind of structure, you can use traditional tabular data and do stuff with that. But often we don't want to just apply these to tabular data. We want to apply this to all kinds of other data sets. In particular, images are exciting because there's a lot of things that either are images or can be made to look like images. And so if we no information, if we can make assumptions about the structure of our data. So if we have an image, we can assume that if we're looking for like a cat in the image, the cat could be anywhere in the image, and that the cat will have similar structure to it. It will like have ears and a face and whiskers and whatnot. So we can learn features that will search the image for that for that cat. And in this case, we'll do a convolution, which basically multiplies weights by the image, and then you get a sum value. Sometimes those features occur on different scales. So if we don't want to, we can make the convolution filter bigger, but then it's more weights to learn, which makes the model bigger and harder to optimize. So what we can do instead is we can average or take the maximum of a given area and then apply the same convolution filter on top of that. And if you repeat this pattern a bunch of times, you can get what looks like a neural network. So in this case, we take a radar image of a storm, and then we apply our first round of convolutions and pooling. And what we learn is basically you have different filters that key in on different aspects of the storm, some on the storm itself, some on the area outside the storm. And then as we go deeper into the model, we can learn more abstract combinations of these previous features to the point where we can then associate those with, say, the probability of severe hail or some other impact. In this case, is like keying in on like kind of this part of the storm, which is kind of near the updraft, where the hail is likely to be occurring. So that's a basic convolutional neural network. And in that problem, we're basically going from an image to a single outcome. Sometimes we want to go from images to other images, or images to other kinds of forms of data. And so the kind of popular way to do that now is what's called encoder-decoder networks. So the encoder network, you take whatever your input data are, you transform it into some kind of latent vector. And then that latent vector, you can do stuff to it, and then you can decode that latent vector into the thing, either the same kind of thing or a different kind of thing. So one way to do this is with a thing called a UNet, which is an image-to-image network. The idea with this is you kind of basically like learn features at a given scale, and then you send some of those features down to lower scales, but then you also send the same scale features across the model to the other side. And so it can get information but in two directions. One nice property of gradients and like the back propagation is that the gradient at a given point is the sum of all the gradients that come to it. So you can basically make arbitrarily structured models that can feed information from different components and sum them together. We can also have it predict multiple things and do all kinds of other fun stuff. We can also take sequences of images of like text or time series of say weather data and go from a sequence to another sequence. And we can do like kind of crazy things like take text and generate images based off the text. So this is kind of the underlying algorithm for things like DALL-E or sort of the image-based ChatGPT models, where you like draw me an image of a corgi playing a trumpet. It can, even if it doesn't have any, it has images of corgis and has images of trumpets, but by like interpolating between the two, it can make something that contains both, and then sample from the space of those combinations. And so this algorithm, of course, has been getting a whole lot of attention recently, and it has its own issues like making sure hands have 6 fingers and stuff, or making sure they don't have 6 fingers. So with kind of the introduction to neural networks and images in mind, what aspect of weather data do you think is the most challenging issue for off-the-shelf neural networks designed for images? So if you want to take our like we want to apply these, like, let's say UNet to our weather data, which of these could be probably the biggest source of problems for the model? Earth is an oblate spheroid, not a flat rectangle. B, some important weather variables are exponentially distributed, not Gaussian. C, Earth system processes evolve on different timescales. And D, many weather variables exhibit fractal behavior with structure continuously varying across scales. So of these, which do you think is the biggest challenge that we face with if you want to use a neural network?
Here it is for your answers.
it sounds like there's a lot of A's and C's, and a fair number of D's, maybe fewer B's. I think to some extent, we run into problems with all of these in terms of trying to fit like neural networks to weather data. Like the A is a particular issue if you don't. It's one that can be addressed, but if you just apply it off the shelf, I think it is. If you're not attuned to how weather is moving around the world, and you just apply like an off the shelf model without accounting for spherical geometry, it causes a lot of problems. C is that that's maybe the biggest one that we're, I think, currently running into with, especially with the AI weather models, is that especially even in the atmosphere, the stratosphere evolves at a different time scale than the troposphere, but sometimes where the boundary between the troposphere and the stratosphere varies depending on where you are on Earth. And so sometimes the models, like, it can do great in the troposphere where things evolve pretty quickly, but then the slower stratosphere processes that like struggle to get a good gradient on those. D is definitely also can be an issue where there isn't good scale separation, but we still discretize with the pooling between different layers. It's the models do surprisingly well even with this, because I guess the data is already somewhat discretized, but if anyone can come up with like a nice continuously varying way to handle that, I think that would also be a good challenge to address. B is also a problem we run into to some extent with things like precip and wind speed and other variables that are positive definite and exponentially distributed. But we're finding some ways to address this issue, whether it be transforming the data into a more Gaussian distribution or bigger ensembles to sample the tails better. So it's I think it's definitely a challenge, but I think it's one that's easier to overcome. So finally, I'm going to kind of talk about some of the weather applications we're working on. NCAR in the space of these like neural network, and especially neural network methods in particular right now. So one framework we're working on is in the AI weather prediction space. We have a new modeling framework we're in the process of, we're going to be releasing very soon, called CREDIT, the Community Runnable Earth Digital Intelligence Twins. So we set up a system to train and run our own AI NWP models over the globe. There's a number of other groups that have already done this, and so like Google and NVIDIA and Microsoft and kind of smaller groups like ECNWF, which is the kind of European Center for Medium Range Weather Forecasting. With our system, like kind of one of the things we're doing is trying to capture those more like faster timescales and have a model that's still stable at those faster timescales. So you can see an example prediction from the model where we evolve things like you see the diurnal cycle temperature. You can see small scale variations in the wind fields. You can see kind of terrain impacts. We also see some artifacts like at the poles. We were having some issues with the model. And sometimes we have these like high frequency waves that pop up in random locations. So there's a lot of cool structure it's learning. There's also a lot of challenges we're still running into with fixing some of the artifacts. But we've been able to run it really fast and also run this model out for a year without it blowing up. So we're pretty excited about it. Another system we've been working on is kind of in the space of bias correction and predicting extremes better. We're using these diffusion models, which basically take kind of quasi-random data and then repeatedly sample them to kind of generate realistic fields with structure at fine scales. We combine basically a transformer model and a diffusion model to generate basically larger ensembles that have basically skill at predicting really extreme precipitation better than the original ensemble we're training on, and better than other methods for kind of correcting precip forecasts. So we can generate like different scenarios from just a smaller subset of scenarios. And then you can see what this looks like in sort of the neural network vector space, where the true example is the star. The blues are like the original physics-based ensemble, and then the yellows are just doing an initial correction of those blue members. But then with the red, when you go further, and you want to take those. You want to sample the space better, so we use our diffusion model to kind of generate more samples, and that gives us better scores and better uncertainty quantification. We can also do uncertainty quantification through other neural network methods. So in this problem, we're trying to predict precipitation type, the winter, so whether it's rain, snow, freezing rain, or sleet. And we can account for different forms of uncertainty, so both the uncertainty in the underlying data that we're using to train the model, as well as the uncertainty in how the different ways the model could be fit to the data. And when we investigate the uncertainty, we can see the physical structures that pop out. So in this case, we can see with increasing uncertainty, so the lighter colors point to basically situations where in high uncertainty cases, we were closer to the freezing line, which makes a lot of sense. But also in terms of the structure of our sounding between the freezing rain and the sleet, we get very different predictions with small changes in temperature. We can also look at kind of in the space of using machine learning models to understand properties of our data. We can take simulations of thunderstorms, and we can group them into different kinds of thunderstorms that have different hazard properties. So we can discriminate between supercells and squall lines and disorganized storms, and then when based off these predictions, we can see that depending on the type of storm, we're more likely to get certain hazards. We can do this in different ways, some that require hand labeling every single storm with a label before training the model, but also we can train a model on another task that isn't storm mode and still get a latent vector that separates out the supercells and the squall lines. And then we can kind of cluster or group similar latent vectors together and then have a human only kind of look at like a bunch of storms at once and say, oh, these mostly look like supercells, so we're going to call this the supercell group. So this could be used for other applications where it's a lot of work to hand label storm or hand label data and kind of help you dig and get greater understanding of what kind of the properties of the things you care about. Going beyond just like predicting weather properties, we also want to map from weather predictions to impacts. So in this application, we're predicting the probability of tornadoes as well as generating synthetic tornadoes based off of the weather environment. And with these synthetic tornadoes, we can then overlay where they happen over population data and see like how many people were affected by that synthetic tornado. And then given that we don't know exactly where a tornado is going to happen at a given time, we can like basically pick an area and put the synthetic tornadoes over different parts of the area and see how much the impact varies. If you do this systematically for a given event, you can see how basically the probabilities of both the tornado itself as well as how many people are exposed to it will vary. So one of the things you see is like you're more likely to be exposed to like have a large exposure to a tornado in larger cities, but also where the tornado tracks are expected to be larger and more likely. So when you combine all that, we can kind of dig into how does the uncertainty vary over time. We can also look at different areas and see in some areas you have, depending on how people are moving, more people are there during the day than at night. And in other areas, more people there at night versus the day. And some of those areas of people are much more concentrated. So potentially during the daytime, a tornado, if it goes through a given city, like it's less likely to hit a highly populated area because there's fewer of them. But if it does, the impact would be greater. So this is potential information that people could use, like decision makers could use if they know a tornado is going to happen in a certain time frame. Basically, like prepare to handle those impacts faster, so that you could get, like say hospitals are appropriately staffed, or you can get firefighters or other rescuers to a given area and make sure they're on call, so they can speed up their response. With all these cool applications of AI, there's also some ways these AI systems can go wrong, and not, of course, we've seen a lot of this not just in especially in other application areas of AI, but weather and climate applications are also not immune to this. And the issues can come from with how you collect your training data. especially if you have like non-representative training data. If you say only gather your data in one part of North America and you want to apply it in like South America, you're probably you may not like the model may perform very poorly. There's also adversarial data that can come up and be an issue if both intentional and unintentional. The models themselves, how you set them up, and how you if when evaluating or lack of evaluating can cause them basically models to maybe learn the right answer for the wrong reasons, and then generalize poorly or produce the wrong predictions at the wrong time. I think there's also issues with just like if you deploy AI models widely, like the demand for their use can then lead to basically having to build a lot more computational infrastructure, which when you're first interested in saving compute, now you're causing a lot more compute use and increased CO2 emissions and water usage due to all the computing and power usage. This was written before ChatGPT, but it's definitely we're seeing this becoming more of a problem. There's also sources of bias in the models from every part of the AI modeling cycle, and some of these, I think, sources can be mitigated with better training strategies and better and like closer interaction with different users and people who are potentially affected by it. But not all these biases can be completely taken away. But at least if they're acknowledged, we might be able to come up with better systems or other ways to mitigate the harms. So I have a couple of papers about a co-author on that I encourage people to read if they're interested. And so this question says I have a correct answer, but I was kind of curious to see what the audience thinks. What of these some of these different weather AI application areas, what's the most interesting one to you? So A is ethics and biases of AI weather prediction systems. B is AI numerical weather prediction. C is estimating severe weather impacts from weather and societal data. D, understanding the sources of uncertainties. E, improving the prediction of extreme precipitation. And F, identifying environments with high wildfire potential. It's good to hear a diverse set of interests, and all these are, I think, challenging problems and ones that need more attention. So with that in mind, like you may be wondering, like this is really cool. How can I work on this as like a career or other pathways? So at NCAR here we have some. So if you're a undergraduate or graduate student, we have some internship programs that basically they're competitive programs that kind of we solicit applications starting in the fall. So there's I tend to sponsor people through the middle one, the summer internships in parallel computing science. We also have, if you're interested in kind of more general or system science internships, there's the NESC program. The super program. There's also the SOARS programs run through UCAR, which is targeted at kind of underrepresented groups in atmospheric science. If you're a grad student, we also have visitor programs where you can come out to NCAR, work with scientists here for usually a couple months, and then especially if it's on a project related to your dissertation or graduate research. We also have an advanced study program postdoctoral fellowship, which is another highly competitive program, but basically you get 2 years of funding to do whatever research you want after you complete your PhD. And if you're not an atmospheric scientist, NCAR also hires software engineers and people with all kinds of expertise to work on different problems. And we work with like the kind of government weather agencies, other weather agencies from different countries, private companies. There's a very fast growth, I guess, somewhat fast growing private weather space now, and also increased interest on the climate side too. So for the person who want to make a lot of money, you can there are in the space of like finance, so like things like reinsurance and commodities trading and things like that. There's a lot of interest in weather data. Tech companies are all building their own weather models now. and internationally, I think there's a lot of room for growth. I'm involved with the World Meteorological Organization, and there's an early warnings for all initiative that it's looking to help support whether improve the level of weather warnings globally and provide systems to do that, including AI systems. So it's an exciting time. There's a lot of changes going on, a lot, I think, opportunities to contribute. With this program, you're able to get some practical experience with some of these weather and climate data sets and try some AI methods on them. So with that, I'll leave my kind of summary slide here, and if you have questions, feel free to reach out over email or to me on social media, and happy to take a few more questions.
Fantastic. Thank you very much, DJ, for this great and very insightful talk. There are various questions on the Discord, which I will share with you.